But I joined Maptek I've only got half an hour, so I won't go on too much, but I joined Maptek in 1989, 88 in Perth, opened the office in Perth, and we built it up, and I left in 2002 to go and do things elsewhere, doing some work at the Water Corporation as a GIS person, and then to Freeport as a consultant, Vulcan consultant, and then extended time a little bit at BHP, but about 10 years at Rio Tinto in innovation, and not particularly related to Vulcan. But some of the things that I'll talk about today are some of the aspects that came out of my work at Rio Tinto and my early work at Maptek, yep. Okay. So I'll start talking about digital twinning and what is digital twinning. And I don't know, has anyone really had much to do with digital twinning or studied or whatever? Okay. Oh yes, we don't. So digital twinning is a concept of replicating what's happening out at an operation, mining operation or any production environment into a virtual environment, and that fitted in pretty well with some of the work I was doing at Rio Tinto. The concept started in 2002 out of a university, but in fact we were doing it at Maptek back in 1990s when we were using Envisage, which is one of the Vulcan products, to sort of bastardised version of that used by the Australian Navy to track all of the ships and aircraft in the First Iraq War, and we had installations at Garden Island here as well as over in Sydney, as well as in the Gulf War, and we were the only system that was able to handle the amount of traffic that was happening throughout the activities of all the ships and all the planes that were going on in that conflict. They since went to a microstation-based system which doesn't do anything as well. So as I said, the digital twin is a virtual model of a process, product or service, doesn't matter what it is, but it's almost an exact replica of what's going on in real life, and all the implications with networking and data storage that's involved with that. So it's used for for a range of things, but essentially allows you to look at what's going on in an operation in real time with regard to the stats that are going on. Because we are collecting a lot of stats, whether it's from Internet of Things or whether it's from SCADA devices or in fact the things that are happening in a geological model, or in fact in this case what surveyors are doing. And it does allow you to create in a range of environments, create a way of reporting on what's going on in the system, to allow you to develop real-time analytics and real-time AI type situations, analysis to affect your decision making in a mining environment. Oh, God had come in. So here's some sayings you can read if you like about what digital twinning is, but it's been trying to be implemented by it's me, it happens to all the time.
That's all right, we'll just keep going.
And it's part of the 4.0, Industry 4.0, Agenda 4.0 is the Industrial Revolution 4.0. So that's what we're supposed to be involved in. I don't know if you know it, but we're actually in the fourth Industrial Revolution at the moment, as specified by somebody somewhere. And I don't know if this is going to come up, because I don't know if you've been copied across. No, it's okay. No, I'll just let it slip. Next one. So what that video was going to show was the fact that it was actually a jet turbine, and a jet turbine that morphs into a virtual version of it. Now how that works is, and that replicates what goes on in a mine site or what goes on in any plant. Instead of having SCADA diagrams with issues of knowing what's going on, what's going off, what are being reported at certain places, it does it in a holistic sense across the whole environment, as much as the mining environment as you want to do, or it could be a small part of it. We have a small digital twin happening at a BHP site in Brisbane, in Queensland, where we are doing something to do with coal traceability or whatever. I don't really know much about it, but we are working with a major mining company in WA, working on developing a digital twin, and I will discuss a bit more about that on some of the important things that we can actually, which is relevant to surveying or surveyors. But it's essentially taking all of the data that is coming out of that mine site that can exist in a digital form, whether it's Internet of Things data, or whether it's people doing mine planning, or whether it's surveyors doing drone pickups, whatever. It all goes into a central repository, and those central repositories have links to each other, or potential for links to each other. So it's an evolution in growing a system that allows you to have a virtual environment that replicates what's going on at the mine site. It's interesting that a lot of the mining companies, Rio, BHP, all of them, in fact, the iron ore ones, have a remote operating system, a centre, but they don't really, certainly in my time in certain places, have a digital twin environment. They have parts of it that might be considered like that, but not a holistic sense of what's going on. And once you have a holistic view of what's going on in a mine site, you can actually do some clever things with some tools that you can develop into that to detect, using machine learning or other aspects which I'll talk about later, to actually see what's going on on a real-time basis. There was a classic film that was in the Rio Tinto archives of what's going on, and you gave the impression that they were reacting dynamically to what's going on the mine site, but that was only happening in a very small part of it. You're supposed to be actually be able to looking at, there are things running around the ground, and no one went out of the pit because it was too unsafe, but they had little scampy things that were running over the ground, picking up grade's not good enough here, let's go mine over here, such and such. But it didn't actually, hasn't actually panned out that way for a number of reasons. The technology wasn't there at the time. Certainly a lot of the AI technologies have come up since the early 2000s. But a key part of having a virtual environment which represents what's going outside is the visualisation of it. Now, visualisation is very important. You can put on your VR glasses and get in there and get dirty with your, well, not dirty, but get in there. But the other one is to have a collaborative virtual environment where people can discuss things. And one of the issues I used to have at Rio was the fact you get 4 or 6 mining engineers discussing a problem, and they couldn't resolve it because they're all of the same mindset. But you throw a surveyor in there, or an accountant in there, or a geologist, maybe not the accountant, and you'd resolve a few solutions quite quickly because you have an alternate person giving a different perspective of what's going on in that environment. So the visualisation that I developed at Rio Tinto, we developed at Rio Tinto with Mark and those, which for its time, 2006, 2007, was way ahead of its time. And I think it got canned, but it's surviving in some other format at the moment. But those virtual and augmented, there weren't so much virtual environments in those days because we didn't have the hardware to carry it through. But we did have 3D environments that were shared around with other people. So and they were based on games. But we didn't, at Rio we used the Gamebryo engine, which is still around, but wouldn't be the one you choose today. But we are developing, and we have pretty much developed an environment that's based around, well, Unity, but we're moving more towards a Unigen environment, which is a network environment that allows you to actually live in the environment, if you like, and talk to people in the environment and discuss problems and do some redlining and so forth. It's important for strategic planning, but also important for real-time planning as well. And I'll talk about that, but you can have some bots in that environment that can actually say, what's the latest information from the plant, or how's reconciliation going? You have these bots that can run around and give you that information, be part of the conversation. That's, believe it or not, that's a technology that is around at the moment, just waiting to be used in the mining industry, and we're certainly demonstrating that. And of course you can have lightweight WebGL systems, so you can be walking around the pit, with an iPhone or an iPad or whatever, and seeing really what's going on either below the ground or what's happening with regard to trucks. You know, maybe you have it so the truck is coming along, it's not going to run you over, but you're unlikely to be in that environment anyway. So now I just want to talk about, if you've got a feeling for what a digital twin is, it's just a clump of data. Clump of data is nothing until you can turn it into information, and into knowledge, and then into wisdom. The idea is to get to that wisdom stage as far as possible. Not many people actually get to the wisdom stage, and that's not putting anyone down or anything, or any company down. It's just a difficult thing to get to. We're great at collecting data. In fact, you're data collectors. But in fact, when you take it to the next level, you start throwing it into information, you give it context, and then you need to build that context into a bit more stuff and to turn it to knowledge that you can make decisions out of. And decision making comes out of knowledge. And that's theoretically decisions go into wisdom. So with complexity science, and I studied this at MIT when I was at Rio Tinto, which is great. Complexity is a way that the world has got so much data in it, and there's so many linkages that you cannot know what's going on. I gave a lecture at Rio Tinto when I actually said to some senior managers in a big meeting they had that they have no impact on the system because they're too far away from what's going on. And the system is actually running by itself because it's almost like a chaotic thing of what's going on. BHP and Rio Tinto and all mining companies have that, where they're actually a chaotic view of what's going on eventually comes back to a system of self-organisation where on a mine site people will know who to talk to who's better than someone else, and you will get a system working out of that. Structure on top of it is important, but it's not necessarily what's going to make the mine work. And the same thing exists in office environments. And you can't look at a system by just breaking it down into, like if you were to take a plant, for example, and then find out, oh, this plant is made up of leaves, flowers, stem, roots, and then you say, well, that's what a plant is. And then you can turn it down, well, actually, if you look at it, it's made up of this amount of carbon, this amount of hydrogen, this amount of oxygen. There's no way in the world, if you knew that what the plant's made of from an atomic point of view, that you could actually go and build a plant, because there's a lot more to it. It's like 2 + 2 = 5 or 10 or something like that. And that's what complexity science is about. You can't look at a problem from a reductionist point of view by pulling it down. And that's how a lot of computer systems are developed these days. And I'd say the last century, that represents the technology of the last century by breaking it down to a reductionist view of saying, well, we do this, we do this, we do this, we do this. But there's a lot of feedback loops that are going on around the place that are changing the ultimate outcomes. And a lot of that we actually intuitively do in our brains, because we are non-linear thinkers, we're Bayesian thinkers, and we are able to look at problems in a different way. As soon as you start to turn it into a workflow to a certain degree, in a big operation, then we start to lose grasp of that feedback loop that are constantly going through, changing the outcome of what might come out of the final result. And as the system becomes complicated to complex, and like a car is a complicated thing, but it's not complex. We always know it's going to start, we always know it's going to do this, we always know if you don't put oil in, it's going to do that. But it's predictable. In a complex environment, it's not predictable. It's non-linear in the sense that you can't always get the same result every time. And in mining, especially the larger mines, that's a complicated operation. Pilbara, whether it's Pilbara blend, trying to get everything together, is not a complicated problem. It's a complex problem. You can't solve it with linear techniques. And some of the aspects of complex systems are, you've got to have a system that's adaptable to what's going on around it. And so adaptability, and that's the generation of complex adaptive systems, a system that actually moves with the changing environment. And that's one of the key advantages of a complex system. But one of the major things that can come out of a digital twin environment of this massive amount of data and this intelligent way of looking at the data is the idea of emergence, where emergence is the derivation of new techniques or new ways of looking at the same problem. Now that's not necessarily coming straight from AI or machine learning capabilities or other intellectual advanced techniques. It can come from collaborative visualization, a whole bunch of different people at different locations looking at the same problem and trying to solve it. And that solution is not necessarily, yeah, we're just going to do that because that's our reductionist view on things. It's a different way of looking at it because we can have a whole bunch of views that will taint it. And because we're the way we are as human beings, even though if I say to someone, Nick, I can throw an idea at Nick and he'll disagree with it. But because I've said it, it's actually implanted in his brain. He can't forget that. He might still disagree with it, but it's stuck there. And that will be part of a conversation where everyone's implanting, but that's the power of human beings. They're non-linear Bayesian thinkers. You can say something to someone and they will disagree with it, but they won't forget it. And if someone else says it, it'll just evolve, and those ideas evolve. And that's the power of getting a whole bunch of people working on the same problem. And if they have a different slant on things, and without being racist, certain aspects of the world have a different way of looking at certain problems, which is really quite powerful when you actually look at the potential solutions we could get. Hopefully climate change will get down to that one day. So, I don't know how much time's going. Oh, okay, so going into a bit of, these are the complexity techniques we use to solve problems. Now this is 5 minutes.
Left.
Oh. Okay.
Sorry, 20 minutes left. Apologies.
You can't do that. I'm an old man with a tricky digger, a tricky tricker. These are the techniques we use at the moment. Some of them are more prominent than others in getting as much out of the data as possible, moving it from information into knowledge or from knowledge into wisdom. And machine learning is the obvious one. Machine learning is really just in its basic form, it's just a serious amount of statistics or detailed statistics. There's some clever techniques there, like the random forest technique, which is quite clever, but it's not earth-shattering. You can read it, you can understand it. But if you go and look at a neural net, for example, where you've got, say, 24 layers, you have your input layer and you have your output layer. You've got no idea what's going on between those 24 things. You could probably sit there and work it out if you've got 3 or 4 lifetimes, but you just know how the result sort of comes out. So that's sort of chalk and cheese of machine learning to the more adventurous artificial intelligence. The other way is looking at things from a non-linear analysis and dynamical system modelling. Now that's a new field of study, and actually industrial study, of looking at problems and how things evolve in a mine site over time, but laterally as well within a series of mines. And I don't want to talk about it too much. But in deep learning, we have been successfully introducing convolutional neural networks in estimations. But we've taken at one mine site the ability to take drill hole data, to do some analysis with that drill hole data, determine where there's some problems in the drilling, solve those problems, or suggest solutions to those problems based on looking at the whole set of data. So it's machine learning. We prepare that data, we go then into a geological modelling phase where we go and use a neural net to create domains, and from those domains we can then go and do some estimations. And the estimation is not a kriging technique, it's a neural network technique. And essentially that flow takes from, I think most BHP, Rio Tinto, FMG, Roy Hill and some of the others would take about 2 to 3 months to do an ore reserve estimation based on the new data coming along. We've got that down to less than a day to do that. The geological modelling may not be the most perfect thing to start off with, but the advantage of the stuff that we've done so far has been pretty impressive, and the estimation is as good as you get out of kriging. But of course we're spending a lot of time. We're actually releasing that in about 2 months, but we're doing a lot more research into that. And the research comes in areas of particularly gold mining and having geological structures that aren't being picked up within the range of the drilling. So you need to make an interpretation in that. A geologist needs to make that interpretation, and I'm a geologist and I can say that. But you need new techniques to do that. You need to be able to say, we're drilling a hole in, say, Stewart Shelf, and the kind of ore body we're looking for is an IOCG deposit. So the number of, we only have 10 or 15 drill holes, and we've got some mineralisation. We can then add an assertion of what an IOCG deposit is, or a beachstone deposit, say down in the southwest, or wherever. That we have a different model for each type of deposit. We can then influence the development of that neural net, and that's using a dynamic graphs convolutional neural net, or there's some other techniques we're working on as well. And there's another one where you get neural nets to fight each other come up with a better solution, and that's the generative adversarial convolutional networks. Now that's a big area of recent research that's happened since probably about 2012, 2011. A friend of mine's a stockbroker, and he was trying to float a company in the 2000s and on artificial intelligence. And I thought, I don't know how to do that. It's only a new field for me to jump into. And then about 2013, 2014, I was thinking about that and actually working with a guy that was developing some techniques there, and I thought we could actually float a company with this. And he said, nah, artificial intelligence, old history, nothing's happening there. But nothing can be further than the truth. Artificial intelligence through neural nets and through other techniques is an exploding area that really we as a group have got to take advantage of in some of the roles that we do. Moving on to genetic algorithms, I was going to do a PhD on, I'll forget that. Yeah, based on, it's called gene expression programming, based on how a gene actually goes through its replication sequences, developed by a biologist in Spain. And I was going to do a PhD, but I didn't in the end because it looked too hard. But genetic algorithms, there's thousands of them based on the way that the environment works, whether it's ant optimization or some other bees, for example. That people create these optimization algorithms based on those. And it's genetic in the fact that things grow and die, but they evolve and they evolve and they evolve. Years ago, I saw one about a yacht that was travelling. They were trying to city America's Cup. And they were trying to develop the technique of winning an America's Cup with that triangle network. They're starting off with a boat that didn't even know how to sail, but you know, to go somewhere and then die, and a new one would start off. And bit by bit, you see that some things were just sitting there doing nothing, but a couple would eventually go around and win and do something optimal potentially. And we do use that in the evolution scheduling algorithms for short-term, medium and long-term scheduling or strategic scheduling. And it's amazing. It's really quite clever the way that things happen in that environment. But my big interest is in multi-agent systems. And multi-agent systems, going back to Rio Tinto, did a great project at Rio Tinto on trying to optimise the selection of a dynamic environment to get the best grades to build a pillar blend environment. Because everyone does a schedule based on what a block model is, but what actually happens in the real-time environment is where they say there's going to be a grade of 60% or 63%, might be 55%. What do you do? And or it might be high in phosphorus, and you've got different mines all around the place that have to come together to form this Pilbara blend or whatever optimisation thing you wanted to build. So we had agents, and agents were people that little computer programs with not a lot of sophistication in them that talk to each other, argue with each other, get controlled by a certain superior agent on top. And the superior agent on top says, "What can you give me?" And they'd go, and all the people from all the mines, all the agents from all the mines would come back and say, "This is what I can do." And they go, "Well, that's not going to make anything. That's not going to work for us. We're going to lose money on this. Rethink about it. You're low on phosphorus, you're high on phosphorus. Come on, do something different." And they would go back and rejiggle their stuff and come back with what they considered was a feasible way of moving forward. And in fact, those agents right at the very tip of the at the mine face would be doing little optimizations using Cplex or some other optimizer, and which, if you've got a small problem, Cplex is very fast. If you've got a massive problem, Cplex just won't work. It'll never get to a solution. But that was getting to a 98% solution very quickly. And in fact, when you look at it, we are all agents working in an environment, working together, sometimes adversarial, sometimes in conjunction with each other. And it's amazing how it's non-linear, it's non-predictive. It depends on the situation, depends on, in some cases, in a mine, depends on how the mine manager is feeling at that time. Yeah, I'm not going to do that because I can't be bothered. It's not affecting my KPI. Why should I care? But if you can turn that into a system of people, of agents talking to each other, you can get an effective understanding of what's going on because there's no emotions involved. But this only gets us to making suggestions, and we need to get to the next stage of making decisions. And decision theory is a whole new area that's not getting much of an understanding anywhere in the world. I did meet Gigerens at the Max Planck Institute technology or whatever in Germany. He's the world's foremost man in decision theory. And decision theory is how we act under certain circumstances, under certain data, certain sets of data, and in certain environments. And that is something that's trying to be computerized at the moment, but they're having a lot of trouble with it. And the other ones are networking systems, which I won't go into, and Bayesian. We all learn classical statistics at school. The Bayesian statistics is a different way. It's a lot older, but it's one of the top 10 technologies in the world for solving intuitive, non-intuitive problems. And in fact, we are all Bayesian thinkers. Our brains are Bayesian thinking, and that's all based on precedents. You know, the example is it going to rain tomorrow or not? Well, it's 50-50. So it's going to rain, it's not going to rain. But because we are Bayesian thinkers, or we know there's precedents in that, we know that, well, if it's in the middle of winter, we know that there's a good chance tomorrow might be raining, as opposed to summer where it's not. So there's precedents that we have in our brain, or within a system that we're using, that says, well, the chances are a bit different. So it's a strange way of doing things, but it's mainly done for, originally for gambling type of effects, but it's very powerful. It helped in World War II for the Enigma codes, and it's helped actuaries in determining insurance premiums and so forth. Now, I'm going to talk about, because that's decision theory, and that's what I'm talking about, digital twinning. But the key to digital twinning, and this is where it's getting interesting for you guys, because I probably went a little bit boring, is that how we're going to store this data. And for a surveying group, you've got lots and lots of data coming in at all times, and how are you going to be able to keep that together? Or the same with the block modelling system, or the same with all of the data that's been collected from a plant, or from the fleet, or from wherever. So the way we've looked at things, and this is going to make sense to you, because a company I used to, well, we were doing with it when I was at Rio Tinto, but when I left Rio Tinto with a friend of mine, we did a lot of work with octrees, data structures. And today we tend to break things into a cube, then break it up into little cubes, little cubes, little cubes, little cubes. In some cases, we can go into subblock models, which is what Maptek's doing in the old days. Still today, but we're moving forward to, and you can actually have, with a grid-based system, and this is actually, looks like a grid-based system, but you can actually get the perfect replication of what's going on a surface, whether it's underground, whether it's a surface in the ground, or sorry, on the surface or underground, by just breaking things down into smaller and smaller pixels, or if you go into 3D, into voxels. And you can see in the distance that hill structure looks pretty reasonable, but when you get closer, it looks a bit crappy. And so you see that bit by bit, that's the same thing replicated all the way down without any breaking it into anything. It's a pure 3D grid, X, Y, Z grid, or IJK. But when we start talking about octrees and their equivalents in quadtrees, which is something that got developed in the late 70s, and in the early 80s I was interested in it, and at Maptek in the early days, 1988, we had octrees, and I was excited about it, but we got rid of it to chase data mine and went to the current system, which is still good, but not as optimal as what octrees are. And that is breaking the world down into cubes as you need to break it down, but as you need certain resolution in certain places, you keep breaking that cube down into smaller, smaller pieces. And in a 2D sense, that becomes a quad tree, which can go to n trees if you like. So you can start having things that are, you can throw time in there if you wanted to, although time's not a dimension, but you can throw time in there or other things to make up dimensions for very complex data sets. And it's stored in this sort of way, which is not that interesting, but that's how it's stored. But it makes it very easy to get from one small cube right back to where it comes from and to find its relationship with that around it. So it becomes very efficient to deal with things. And this is the standard Stanford bunny, and you can see that it's a fairly high resolution rabbit, but you can see that it doesn't need a lot of cubes to define that structure. Compared to if you just did a big 3D cube at the smallest resolution, which might become a very unwieldy but very efficient in accessing that type of structure. Octrees aren't as fast as pure grids of 3D XYZs, but they do have some advantages. They are almost as fast, but they cut down on the amount of information you need to store. And we have developed a massive spatial data structure, which is in competition, not yet, but will be in competition with groups like Potree, Euclidean, ultimately Point Tree, but we do things differently. There's no, where we're dealing with opt trees, quad trees, and n-based trees. And the advantage of having these things together is they can interact with each other so quick, so dynamically. So we can, I can interface a terrain as an opt tree with a block model, an underground block model, as an opt tree instantaneously, and get the surface and get whatever calculations we need to do. And that resolution can be whatever you decide. And so it's extendable into any dimension we want to work with. So mostly, let's say for this case, we're talking about fourth dimensional time, and whatever data types we want to use. It's massively parallel and it's lightweight. And I don't know what the next one is, but I'll let that go. It has virtually unlimited storage. So if you've got enough disk space, you can model as much of the world as you want to model, to whatever resolution you want to model. I'll show you some stats soon. And it's a vertical solution where it covers, I don't even know what that means, forget that. But it can exist on a cloud environment, and we are doing our research in a cloud environment using AWS in Sydney, or a corporate cloud, or because a lot of mining companies don't want to put their stuff on a corporate cloud, even though it's more secure, or within a server farm directly, and we have both the cloud and the server farm. We don't have a corporate cloud at this stage. And the interfaces we have is a RESTful interface, so it's exposed to whoever wants to look at it, and RESTful is the most powerful interface you can do at the moment as far as interfacing to other systems. But we do supply Python, C++, SDKs, etc. And we can decompose it into OLAP structures, which is extremely powerful if you want to dump down a block model, for example, and start parading through it in pivot tables on a spreadsheet like Excel. And it's instantaneously fast. Very fast, sorry, instantaneous. Forget that. What we do is we provide a streaming interface so you can visualize it either on a WebGL environment on your iPad or a PC, or into Vulkan, or into MicroStation or AutoCAD if you've got the interfaces to do that. So, and it's, what it means is you can have something that's got, can never get into memory, but will fit onto your machine through the internet very quickly. So as you move in, it'll get high resolution. It's like in games. You don't have the game's not sitting there in graphics memory all the time. It's as you're moving around, things pop up, it'll get greater resolution as you move closer and closer. And it's the same sort of concept, but far more efficient and more powerful. Actually, the concept came from looking at multi-user games where a lot of people share the same interface, share the same data, and you want to look at the same problems together. Who to kill next? It's highly encrypted, so if you're into that. They're the interfaces we currently have into Unity, Unreal Engine, and Unigine. It's multi-user read and write. Supports all of those traditional ways of keeping stuff together. I'm just going through our data storage. So we can use that data storage for block models, 2D, 3D, and ND surfaces. Now, 2D surface can be your terrain, which I'm talking about. In fact, the terrain work we're using with the current mining client is we use the 3D terrain surface for terrains, because 2.5Ds everyone thinks is fine, but when you get to a mine, you do get these convoluted surfaces, which in a 2D situation is probably not a problem because it's the resolution is not required. But in fact, if you're doing geotechnical work and you are putting high resolution pickups from scanners at the side of the wall, then you probably need that. So you can have that in the same environment. And obviously point clouds and in fact drill holes and potentially CAD information. So we're quite comfortable with that. It offers version control and progressive version control. Yeah, I'm not really sure what I mean by progressive version control. But version control means you can know what that model looks like at a certain time. Now, this is relevant for terrain because we have a terrain surface being developed and changing all the time, constantly changing. I'll talk about the frequency of that. But it does mean that if you have a surface there that represents the topography that has existed at your mining operation from starting in 2005 and going through to today, you can actually look at that same data structure and say, show me what it looks like on 5th of May 2012. And it'll take 5 seconds to reset to that position, and you'll get that terrain as it existed at that time to the resolution you specified to start off with. That's what version control means in that sense. Bifurcating version control is like software development where things can bifurcate into certain development streams and come back together. That's probably more important for block modelling and geological modelling. And this is the resolutions we can achieve from this. And this is going to blow you up a bit. We can put the whole of the Pilbara, or we can put the whole of Australia into this structure down to a resolution of 7 nanometers. And it'll always be real time in accessing it, 7 nanometers. Or if you want to go for another way of projecting it, if we had Mars in its real position, the Moon in its real position, and the Earth in its real position in alignment, which only happens fairly rarely, we can model all of those three things together in the same environment, in the same model, to a resolution to 1 metre, right down to the centre of each model. Impressed? But the speed doesn't necessarily change. And but the thing that you'll have to have is a lot of disk space, because it does require disk space. So those numbers are actually they're theoretical numbers, but we have achieved quite a lot of those numbers, and we have modelled part of the Pilbara to, well, yeah, millimetres, but have large scrags of the Pilbara in there from, say, not down here, this place, Exmouth Gulf right across to, say, Broome, and right down to Maptek at a resolution 2 millimetres if you wanted to, and it's fast. So how does this work with the way we're doing things at the moment? For a client we're dealing with, and we have a data structure. We've defined what that data structure is, and that data structure is going to be just going to have the size of the Pilbara, and it's going to have a certain resolution that we're going to want it to go down to. We start off with a base data set, which may be something from Landgate, may be something from a whole bunch of scans that have been put together. A data set you start off with. And continually you start adding live IoT data. Now the IoT data we use is, and we have algorithms for this, is we use the live fleet information of bulldozers, the most powerful tool on a mine site. They're essentially the leaders of the mine site to a certain degree. They control what goes on. Excavators and trucks. And we can actually put everything else in the graders if you want to get into that. But anything that's got a precision GPS position on it, with associated information of speed, and obviously X, Y, Z has the X, or particularly the Z has to be important, has to be accurate, and attitude associated with up and down and so forth. We can actually model that into the terrain, so you can actually sit there dynamically. This is a live feed going into this environment, sitting in an AWS server in Sydney, and you see the bulldozer going along, changing the terrain. And that's a permanent change in the terrain. You can run it back if you like, go and do it a bit off. That's a permanent change in the terrain. And of course, when the truck excavator takes stuff out of the truck, well, we have, and this needs a bit more research, but we know where the excavator's gone based on the information that comes off the excavator, so we can make an assessment of where it's taking stuff out of the ground. It's gone into the truck, and of course we know where the truck is if it's dumping. You know it's gone onto a dump, and that'll be either dumping over the side or dumping into a pile, and then the bulldozer comes along and pushes it over the side. This is demonstrable, and it's really quite powerful. And then when the surveyors come along and they do a drone pickup or whatever pickup they might be doing somewhere, they go and put it into their environment. We have techniques to automate that going into the environment, so it's not saying cut this bit out, cut that bit out. Almost fixed. And it's great. You see all of these things moving around the pit because each one has its own. It's not just one bulldozer. We've got 15 15 or so, we've got trucks going everywhere in this live 3D environment, or sitting on an iPhone, you can actually zoom around and see the terrain moving. You can see a dump being dumped around the side from trucks and being smoothed off to the side by bulldozers. And the terrain is changing. And it's made, we've put in 3 months worth of these feeds that are coming in from these things, and the terrain is actually following it to a degree. Now, I'm not going to say it's as accurate as a survey pickup, but it's the best thing you've got between a survey done at February, for example, compared to April. But there's also then these pickups along the way that do reconcile it back to what it should be in certain areas. That's only in terrain. And of course, survey resolution input that comes in from those periodic surveys. And the uses for this is in collaborative visualization. So we have an environment, a 3D visualization environment, where any number of people can be in there talking and looking at each other or seeing where they're going or walking around in that live environment. So what you see either in your VR glasses or on your 3D monitor or potentially on your WebGL environment is what that terrain is relative, and where other people are, and then you talk to each other. So you have that collaborative thing going on, and you can obviously do reporting on it, and that is available for third-party situations. So we made a Vulcan there that's talking to us and creating this 3D environment, 3D terrain, but it's also available to data mine through this RESTful interface or to whoever might be using some other system. So that's extremely open, obviously open and available. The interesting things, and of course this still represents a timeline where you can go back to any situation you want to look at. You can go back to an accident that might have occurred at a certain period. And as long as you've got and we're talking about the terrain plus the imagery associated with that terrain. Where the imagery is not available, we change the imagery to be what, because we haven't got imagery available all the time. Not yet, but there's ways of sorting that, but you can almost get there. And the interesting thing is, on a geological model and a drill model, on a block model that's created by drilling, obviously, as it takes 3 months to create a block model with the geological interpretation and the estimation, once you've trained the model to recognise the geology and to recognise what's happened in the past, every new hole that goes into it, you don't have to remodel the whole thing. It models itself dynamically because it's got a training set to go with it. So as the modeling's changing, you can imagine the terrain's changing, the block model's changing based on the drilling that's going on, but this is a live environment. This is a digital twin of what's going in the mine plan, the mine environment. Start throwing the plant in there and the fleet in there and the other mobile things that are going on. Reconciliation becomes, reconciliation is the dog's breakfast of mine planning or of operations, becomes something that's achievable, we think. Anyway, that's I think all I'm going to talk about.